In this video, we will look at the uncertainty principle. Generally, the uncertainty principle states neither the momentum nor the position, say represented by the x-coordinate, of a particle can be determined simultaneously with arbitrarily great precision. So since this is the x-coordinate, the momentum has got to be the x-component of that momentum vector. In other words, it's physically impossible to measure simultaneously the exact position and the exact linear momentum of a particle. Let's express this statement in a mathematical way. If a measurement of a position of a particle is made with a precision, let's say delta x, and a simultaneous measurement of linear momentum is made with a precision, let's say delta px, then the product of these uncertainty delta x and delta px can never be smaller than h over 4 pi. Delta x and delta px signify the precision in the position and x component of the momentum measurement respectively. So higher the precision, lower the uncertainty. Sometimes this inequality can also be written in terms of h bar, like that, where we know h bar equals h over 2 pi. We have seen that before. We note here there is nothing special about the x-axis. So in a three-dimensional situation with coordinates x, y, z, then there is uncertainty relation for each coordinate and its corresponding momentum component. For example, the y counterpart uncertainty is written like that. The z component uncertainty is written like that. However, the uncertainty in one coordinate is not related to a different component of momentum. For example, delta x is not related directly to, let's say, delta py, and so on and so forth. So these expressions are known as the Heisenberg uncertainty principle. To understand the physical origin of the uncertainty principle, consider the following setup. Suppose you have an electron, and of course it's moving, and you want to determine as accurately as possible its position and the linear momentum, say through a telescope of some kind. Let's assume this is a powerful light microscope. So for you to see the electron, at least one photon of light must bounce off the electron and pass through the microscope into your eye. However, during the strike, the photon transfers certain amount of momentum to the electron, and this causes the electron to recoil entirely into a new direction. So you see, in the process of locating the electron very accurately, that is by making the uncertainty in its position very small, the photon or the light changes the electron's momentum to some undeterminable extent, thus making the uncertainty in the x-component of the momentum large. So you see, if delta x is small, then delta px becomes very large as to maintain the uncertainty rule, namely delta x times delta px must be greater or equal to h bar over 2. So that is the essence of Heisenberg uncertainty principle. Now let's look at the uncertainty principle for energy. The uncertainty for the energy of a system depends on the time interval, delta t, during which the system remains in the given state. The expression relating these two uncertainties look something like this. Delta E times delta t equals or greater than h bar over 2. One way to interpret this expression is as follows. Suppose we have a system that remains in a certain state for a very long time. So that means delta T is large. Such a system can have a very well-defined energy, or small delta E. However, if it remains in that state for only a short time, small delta T, the uncertainty in energy must be correspondingly larger. Delta E is higher. One can view this delta E as the spread in energy of a particular state. So let's assume we have such a spread in the energy of a state, E1. So the spread measures the uncertainty delta E1. Let's assume the lifetime of that state is delta T1. And you have another state with smaller spread. Let's call it energy E2, and the corresponding spread in energy is delta E2. The lifetime of this energy level is, let's say, delta T2. Since delta E2 is a smaller spread than delta E1, the lifetime of the energy state E2 is longer than the lifetime of that state E1. All this while they are obeying this expression. Let's look at the following problem. The speed of an electron is measured to be 6,000 meters per second. It is measured to an accuracy of 0.004%. What is the minimum uncertainty in determining the position of the electron? Let's first determine the momentum of the electron. Let's assume the component is that of the x component. So the x component of the momentum is the mass of the electron times the x component of that velocity. So the mass of the electron is 9.11 times 10 to the power minus 31 kg. The speed, let's assume it is the x component of that velocity, is 6,000 meters per second, which is about 5.47 times 10 to the power minus 27 kg meter per second. Since we know the velocity or the speed is measured to an accuracy of that much, that means the accuracy of the momentum must also be that much. So the accuracy of the x component of the momentum is 0.004%. So over 100 times that number, which is 5.47 times 10 to the power minus 27. And that's going to give you 2.19 times 10 to the power minus 31 kg meter per second for the uncertainty in the x component of the momentum. Note that the Heisenberg uncertainty principle states the uncertainty in a position or the x-coordinate times the uncertainty in the x component of the momentum is greater or equal to h over 4 pi. We want to determine the minimum uncertainty in the location. So that means the minimum uncertainty is quite simply h over delta px times 4 pi. So the minimum uncertainty refers to the equality part of that inequality, which will give you 2.41 times 10 to the power minus 4 meter, or quite simply 0.241 millimeter. We note h is the Planck's constant with a value of 6.626 times 10 to the power minus 34 joule seconds. So this solves the problem. Problem 2. An atom remains in an unstable state for an average time of 1.5 times 10 to the power minus 8 seconds before it makes transition back to the stable state by emitting certain amount of energy. What is the uncertainty in energy of the unstable state? So this problem, obviously, it's about the uncertainty in energy and time, given by that expression. We are told that the uncertainty in time is that. So we want to determine the uncertainty or spread in the energy. So delta E becomes greater or equal to h over delta t times 4 pi. Let's substitute everything. inside this expression, h is 6.626 times 10 to the power minus 34 over delta T is 1.5 times 10 to the power minus 8 times 4 pi. Of course, the unit must be in joules, giving you the following result. Delta E must be greater or equal to 3.52 times 10 to the power minus 27 joules. Or in the unit of electron volts, it's greater or equal to 2.2 times 10 to the power minus 8 electron volts. So this number in joules or in electron volts represents the minimum uncertainty in energy of that unstable state. And that solves the problem. Thank you for watching.